So first thing, isolate the square root. So now I've got the 4 over on the other side. Having done that, we now can get rid of the square root. Remember, to get rid of the square root, we square both sides of the equation. At this point, when we do the x plus 4, please remember that's not x squared plus 16. Remember, to do x plus 4 squared, you have to do x plus 4 times x plus 4, multiply everything in the first parenthesis by everything in the second parenthesis. And then when we multiply everything in the first parenthesis by everything in the second parenthesis with the x plus 4s, we end up with x squared plus 8x plus 16. Now at this point, we have an equation, a quadratic, that has both x squared and x in it. As you may recall from that problem that we did yesterday, the only way we can solve a quadratic like this is to either factor it or use quadratic formula, and both of those require that we have to start with it equal to 0. So we need to make this equal 0. So do I want to move the stuff to the left or to the right? Well, I always like to keep the x squared positive, so I'm going to move everything to the right side here. So I'm going to move the x over, and I'm going to move the 6 over. Now at this point the question is it factorable? And I hope it is, because quadratic formula would work, but it's a pain. Is this factorable? Are there two numbers that add to 7 and multiply to 10? Yes. Yes. Okay, and those two numbers would have to be 2 and 5. So there's our factored form, x plus 5 times x plus 2. We now can use that to figure out what the solutions are. So what plus 5 equals 0? Negative 5. And what plus 2 equals 0? Negative 2. So there's our two solutions. Okay, we found the solutions. Does that mean we're done with this problem? Sadly, no. Because you notice at the start of this one, we have an x that is inside the radical, and we have an x that is outside the radical. That tells me I have to check my solutions. So when doing the check, remember that you're going to take each answer and you're going to plug it back into the original equation. When you plug it in, remember you're just figuring out what does it equal. You are not moving anything from side to side of the equation. Because if you start doing the algebra to it of moving stuff side to side, you may very well do the same thing that created the false solution in the first place, the extraneous solution. And it wouldn't show up as being extraneous in that case. So you just figure out what it equals. So in this particular case, I'm plugging in the negative 5. Notice it goes in for both x's. And so order of operations says figure out the inside of the square root first. So negative 5 plus 6, that gives me the 1. Then I can take the square root of 1, which is 1. And 1 minus 4 is a negative 3, which does not equal negative 5. Therefore, that one will not give us a valid solution. And so that one is extraneous. Remember our vocabulary from yesterday? An extraneous solution is a solution that shows up looking like it's an actual solution, but when we check it, it's not. Now, the fact that that one did not work tells us nothing about whether the other one will or won't. We still have to check the other solution. So now repeat the process, plug the negative 2 in, and check that solution. So when we plug in the negative 2 for x, you notice we get negative 2 equals negative 2. That is a true statement. Therefore, negative 2 is our only solution. And so the final answer here is just x equals negative 2. And only negative 2. So next up, we're going to be looking a lot at some of the various roots and how we can work with them when we have to actually do calculations. So we're going to be finding the value of each of these without your calculator. Now the fact that I'm already telling you that it's going to be without your calculator should make it actually quite a bit easier. It's not like I'm going to say do it without your calculator and the answer is going to be 1.7325 or something like that. They're probably going to be nice, pretty numbers. So that gives us a point to start from as we think about them. All right, so the first one. What is the value of the cube root of 8? Now when I say the cube root of 8, what that really means, in case you're not used to seeing that, it means what number cubed equals 8. or what number times itself 3 times equals 8. And in this case, 2 seems like a valid choice, right? Now let's actually check it. 2 times 2 is what? 4. And then 4 times 2 is 8. So yes, that does work. So the cube root of 8 then is 2. All right, now let's check number 2. What's the cube root of negative 8? Well, if this was a square root, and we were trying to take the square root of a negative number, we wouldn't be able to with real numbers. Can we with a cube root? Well, if we can, the answer would end up having to be probably negative 2, right? That would be logical in this case. So let's actually check negative 2 and see what it does. So negative 2 times negative 2 is 4. Positive 4. Okay, and then positive 4 times negative 2 is negative 8. So notice since I was multiplying all negatives, since there's an odd number of them, there's 3 of them, we end up with a negative as an answer. So yes, we can take the cube root of a negative number. And so the cube root of negative 8 is negative 2. Okay, number 3, what is the value of the cube root of 27? Well, we're looking for cube roots. So what number times itself 3 times equals 27? 3 does seem likely, but we can go ahead and check it. 3 times 3 is 9. Times 3 is 27. All right, so yes, that does work. Okay, what about the value of the cube root of 64? Well, 4 does seem likely, yes. Let's go ahead and check it and see. What's 4 times 4? 16. And what is 16 times 4? It is 64. Okay, great. So that one works. All right, and for the last one, what is the cube root of a negative 125?
5.
Since it's a negative 125, we know it's going to be a negative number. And the cube root of 125 is 5. So our answer here ends up being negative 5. Now, these sorts of questions, where they're the nice, pretty numbers, are ones that you're actually going to need to know off the top of your head going forward because they're going to come up often enough. I want you to actually write these into your notes because these represent the numbers that you're going to need to actually know by heart beyond just the perfect squares. So there's some perfect cubes, some fourth powers, and even a fifth power there to worry about. And then as you take a look at these, the one kind of odd duck of the bunch is this 1 to the power of n over here. Why is it to the power of n? Because it's just saying that 1 to the power of anything is going to be 1. So it doesn't matter what the exponent is. If the base is 1, you know the answer is going to be 1. All right. Be working on memorizing these. They're going to be coming up often. Now keep those notes handy. We're going to go off on what seems like a slight tangent, and then we're going to pull this and that together here at the end. So at the moment, I'd like you to simplify each of these expressions. We've had lots of practice with these recently, but I want to get your mind moving in this direction because it's going to make our next exercise a little bit easier. All right, so for the first one, a to the 4th times a to the 7th. When I multiply the a's, I add the exponents. So 4 plus 7 gives me a to the 11th there. For the second one, I end up doing n to the 5th divided by n to the 8th. When I divide the n's, I subtract the exponents. 5 minus 8 would give me a negative 3 though. I don't want to leave it as n to the negative 3. So instead, we're going to write it as 1 over n to the 3rd. And then the last one, which actually is really the most important one, is the last one here, because of what we're going to be doing next. When we have a power to a power like this, what do I do with those two exponents? We multiply them, yeah. And so I end up doing 3 times 4, which is 12, so that one ends up equaling y to the 12th. So remember, power to a power, you multiply those exponents. I wanted that in mind because it's going to make this little exercise a little bit easier on you. We're going to find the missing exponent that makes each of these statements true. So x to the power of what squared equals x? Well, in figuring this out, first of all, the x that's on the right side over here, what's the exponent on that x? 1. Yep. Remember, if it's not written in, the exponent is 1. So then, what could this exponent be in here that would make it end up being a 1? Well, we are multiplying them, yep. We multiply the exponent, so what times 2 equals 1? Yeah, 1/2. So x to the 1/2 squared equals x. Because 1/2 times 2 is 1, and x to the 1 is x. All right, so what about the m? M to the power of what cubed would equal m? 1/3, absolutely. And for the b? That'd be 1/4. Okay. Now, in the past, though, we've seen something else, where when we square it, we get x. What else could we put here to square that would equal x? And I'll give you a hint. This one's not an exponent because we just did the exponent. We did it earlier in class today. What can you square to just equal x left behind? What's the square root of x squared? X. And so we could also square a square root to have it cancel out, just like I could square a 1/2 power and have it cancel out. If I then take a look at the m and the b, we could go through kind of the same reasoning. For the m, what can I cube that would make it disappear? Cube root. And what can I raise to the power of 4? 4th root. Now the tricky part. Now it's time to really think, okay, what does this mean from a mathematical perspective? Look at these two statements. Notice both of them are equal to x. What does that imply? Well, if they're both equal to x, that means they must equal each other. But they're both squared, right? So really, since they're both being squared, wouldn't that mean that the stuff inside also must be equal to each other? And so, we can then see that x to the 1/2 is exactly the same thing as the square root of x. The square root of x that you've been seeing for years and years, all that square root, the square root button on your calculator, all of that is actually just a symbol, shorthand, to represent a power of 1/2. And why do we have that special symbol just for it? Because if years ago when you were first learning about exponents, somebody gave you x to the power of 1/2, your brain might have ended up as a puddle in the bottom of your skull. It can just be a little bit too much stress at the very start. So we write it as a square root as a shorthand. But all along, whenever you've been using radicals, they've all just been fraction exponents. It's been the same thing. So the 1/2 power is the same as square root. The 1/3 power then must be the same as cube root. And the 1/4 power is the same as the 4th root. And of course, that pattern would continue on and on. This seems worth putting into your notes then. So please add this into your notes. And the interesting thing about this particular statement that you just wrote down is that this is actually just a special case of another rule. And so I'm going to give you the other rule as well so that we can broaden the meaning of this. If you have something on top of the fraction that's not a 1, that number on the top of the fraction, in this case a, is an exponent on the inside of the radical. So add this to your notes as well. And so now I want to practice using this a little bit. So we're now going to go through these 3 problems together. For each of these, you're writing the expression into radical form. And of course, we're going to simplify anything that we can along the way as well. So start by writing down the 3 problems. So for the first one, we have x to the 1/2. We need to write it as a radical. Now, we've actually seen that one before. is one of our first examples. X to the 1/2 is the same as what? Square root of x. Yep. Now the second one, though, that one's a little bit trickier. Because you'll notice the 24/3, our exponent here, that one can actually reduce a little bit. And so since it can reduce, let's reduce it before we move on. What does 24/3 reduce to? To 8. So then that one is just x to the 8th. Well, since that is x to the 8th, there's no more fraction left in the exponent here. So we don't need to then force a radical upon it. So you would just leave it as x to the 8th in this case. And then for the last one, we have x to the 3/4. We know that since there's a fraction, that we're going to have a radical. So in our radical, which number goes here? Yep, it's the 4. It's always the bottom number that determines which root it is. And so then the 3 becomes an exponent on the inside. So then that's going to be the 4th root of x cubed. All right, now if you can do those, then you can also do these no problem, because this is the same thing. And giving you the radical, just please now write it in exponential form. Go the opposite direction of what we just did. So for the first one, we're looking at the cube root of x. Again, this is actually very similar to one we saw earlier. The cube root of x can be written as x to the 1/3. All right, now the 4th root of x to the 8th. Well, that's going to become x to the power of, the exponent goes on top, the root goes on bottom, so that's x to the 8/4. But again, notice there's some simplifying we can do here. What does 8/4 reduce to? 2. So that one just equals x squared. And for that last one, again, we know it's going to be x to the power of a fraction. Which number goes on top, the 5 or the 2? The top is always the exponent, so it's the 2. The bottom is always the root, so it's the 5. So it's x to the 2/5. All right, now next up we're going to be combining that changing forms between fractional exponents with those values that you need to memorize that we took down to our notes earlier in class. So we're first going to simplify 125 to the power of 1/3. Make sure to write this down as we go through it. When you're trying to do this stuff without a calculator, the 1/3 power doesn't really help us. But if I look at that as a radical, it's much more doable. 125 to the 1/3, that's just the same as the cube root of 125. That is actually something I can figure out, because it's saying what number to the power of 3 equals 125. And that's one of those values that's in your notes. So looking in your notes, that list of values, you're going to need to memorize what number to the power of 3 equals 125. Well, you should see in there 5 cubed equals 125, so it's 5. So 125 to the power of 1/3 is 5. Okay, we're going to do the same type of thing here with the second one. We're going to start by writing it as a radical. Now, if I just follow the rules for changing it into radical form, I'd end up with the square root of 4 to the 5th. And now we get to show you a neat little trick we can do. The square root of 4 to the 5th is also the same as the square root of 4 to the 5th. It doesn't matter whether we take the square root first or whether we do the 5th power first. So if I'm going to try to do this without a calculator, the question is, which of those two forms is easier to do without a calculator? Well, do you know what 4 to the 5th is off the top of your head? Probably not. Do you know what the square root of 4 is off the top of your head? I hope so. Yeah, it's 2. So this is the easier form. So the square root of 4 is 2. And then I can do 2 to the 5th, which if you don't have it memorized yet, you will soon because it's on that list of notes. 2 to the 5th is 32. Approach that last one using the same technique. Go ahead and do that last one. All right, so when doing this last one, again, start by turning it into radical form. And there are those two different ways we can write it in radical form. Which of these then is easier to do without a calculator? Well, do you know what 27 squared is off the top of your head? No. I don't. Do you know what the cube root of 27 is off the top of your head?
3.
You should. If you don't yet, you will soon, because it is one of those values from your notes. It ends up being 3. So we do the cube root of 27 is 3, and then we're going to square that. So 3 is 9. So this one happens to be 9. One thing I want to make clear. You notice that 9 is a third of 27? That was more chance than anything. It is not because of the 2/3 power. Those just happen to be thirds in there. All right. One last set of problems for us to do today. And that's going to be simplifying the product of radicals, or the quotient of radicals. So please write down this first problem. The cube root of x squared times the 9th root of x. And we're going to walk through together how to do it. As we walk through it, you want to be making sure to write out the work that's involved, because this is the stuff you're going to be using on tonight's homework, for one thing. All right, step 1 when doing problems like these. Notice that our roots are not the same type of root. If they were both cube roots, for instance, we could actually take an easier technique than what we're going to use. So this is the technique you use when they're different roots like this. Step 1, take your roots and rewrite them in exponential form. So I turn my radicals into fraction exponents. So now I'm multiplying the x's. When I multiply the x's, what do I do with the exponents? We add them. So that means that in order to multiply these, I'm going to have to do 2/3 plus 1/9. Yep. In order to add them, we got to have a common denominator. Although that's not exactly the worst thing in the world here, is it? Because between 3 and 9, I can make them both 9s. So that first, I multiply top and bottom by 3. That makes it 6/9 plus 1/9. And then I needed the common denominator because the bottom will stay the same, and I add the top, so it equals 7/9. So when I add them, I get 7/9. Therefore, x to the 2/3 times x to the 1/9 is x to the 7/9. Now, one of the little rules and details when it comes to simplifying expressions is that we never want to leave a fraction in the exponent. Unless the problem specifically asks you to write it that way, we don't want to leave it this way. So the last step, change the fraction exponent back into radical form. So then our final answer is going to be the 9th root of x to the 7th. And then we're going to do this last problem here. We're doing the 6th root of x to the 5th over the square root of x. Again, write down the problem and write down the work that we do to get our answer. Just like the previous one, because these are different radicals, I'm going to have to turn them into fractional exponents first. So step 1 looks like that. Now, having done that part, I'm going to be dividing the x's. When I divide the x's, what do I do with the exponents?
Subtract.
Yep, we subtract them. So I'm going to have to do 5/6 minus 1/2 to figure out what my new exponent is going to be. And so yes, once again, we need the common denominator. Looks like 6 would be a nice easy one in this case. So I'm going to turn the 1/2 into 3/6. Remember, I do that by multiplying top and bottom by the same number, in this case 3. Now I can go ahead and do the subtraction. 5 minus 3 is 2, and the bottom stays the same. So it's 2/6. I don't want to go right back to the problem quite yet, though, because you notice 2/6, that reduces. Always reduce if you can, when you can. So 2 does become 1/3. That's what I'm going to use. So I end up with x to the 1/3. X to the 1/3, I can now change back into the radical as the last step. So the final answer ends up being the cube root of x.